In this video, I will be describing a global transport model, GTM, for Krypton-85. It might seem curious to you that a discussion of an Eulerian transport dispersion model is part of the high-split radionuclide applications page. There are two reasons for this. First, a variation of the global transport model described here has been incorporated as a module within high-split, and it is called GEM. And second, the GTM was used to remove background concentrations for several radionuclide measurement experiments that were used for some of the high-split model verification applications. The global scale modeling method was used to subtract the time-varying background concentrations of Krypton-85 from a series of measurements that were made in the United States during the 1970s and 1980s. There were three Krypton-85 experiments, named Accurate, the Idaho National Engineering Laboratory in 1974, and the Savannah River Plant in 1976. These were included in the DATUM project, Data Archive of Tracer Experiments and Meteorology. If you had not already done so, you should review the related web pages for citations and other links. A detailed description of the background subtraction approach was published in Atmospheric Environment. For sampling locations near the release, the Krypton-85 plumes over the measurement sites were unambiguous. However, further from the source, such as the Murray Hill site, variations in the background could be of similar magnitude as those when plumes from the source were present. Variations in background are due to all the other global Krypton-85 sources contaminating air masses that passed over the sampling locations. The GTM was used to estimate and remove the background concentrations. The resulting measurement data, minus the background concentrations, represent the plumes from just the nearby emission source and could then be used for model evaluations. The computer code used to process the measurement data was not published at that time. More detail about the global modeling code follows in the next section. Two steps are required for you to run your own version of the global model. First, obtain the computer code and related startup files. These can be found on GitHub, where you should download the source code, gblmdl38.f. Executables are not provided. Also, the Fortran compiler script, compile.sh, the model configuration input file, default.dat, and the sample file of the annual Krypton-85 emissions averaged over all locations, emission.csv. Citations for where you might find more realistic emissions for each source location are provided in the previously referenced web page. the Krypton-85 underscore global.html. Also, a copy of the user's guide is essential. If you have the G-Fortran compiler available, then just run compile.sh. The default is to run the model on a single processor. Although the code can be compiled for a multiple processor, it does not run substantially faster than the single processor version when using the 2.5-degree meteorology, because most of the clock time is spent reading the data. The second step is to download the meteorological data files. The model is currently coded to read only high-split formatted meteorological data files, and specifically only those on a 1-degree or 2.5-degree resolution global latitude-longitude grid on pressure surfaces. The 2.5-degree data start in 1948, about the time Krypton-85 emissions started, and continue up to the present time. My suggestion would be to start with these data files. For shorter time periods of interest, the model could be restarted using the initialization file created during the 2.5-degree calculation and then running with the 1-degree data for the higher resolution calculation period. The only other initialization option is to define a latitudinal gradient. After you have downloaded all the required files, you can run the code. Your default .dat file may need to be edited to reflect the directory location of the meteorological data files. Only the directory and the name of the first meteorology file needs to be defined if the file name convention used on the NOAA site has not been changed. Subsequent file names are generated automatically, but they must all be in the same directory. Now you're ready to start the simulation from the terminal window. Enter GBL MDL38. As the model runs, it will generate a 3D initialization file daily, gbl3dim.bin, and at the end of each year, a gbl year.bin, useful for restarting in case of a crash. The concentration output, SFC, surface, and then the year.bin files are added to daily, but closed out at the end of each year. Once the model completes, the results for the entire simulation period can be extracted using the con-to-stn.sh script. The underlying program, con-to-stn, is part of the high-split distribution. The script reads the locations in the consites.dat file, and for the purposes of this example, the Krypton-85 time series is extracted at 2 locations away from any nearby sources, one in the North Pacific and the other in the South Pacific. The time series of concentrations is written to consites.txt. These results can then be imported into your favorite spreadsheet program and merged with any measurement data you might have. The calculation results are shown as two continuous curves, one representing the northern hemisphere and the other the southern hemisphere. The individual symbols represent the Krypton-85 measurements at various locations and times. The model prediction curves for those two hypothetical locations in the remote Pacific Ocean, away from any nearby sources, should be closer to the baseline of the measurements, especially those in the southern hemisphere, because most of the Krypton sources are located in the northern hemisphere. For the purposes of this example calculation, the exact emission amounts at each location was not required to obtain realistic results for the background concentrations. An estimate of the global annual average emission rate was sufficient. Notice all locations show the same annual rate. The global average emissions could be optimized further to reduce the difference between the measurement baseline and the model predictions. In conclusion, although the global transport dispersion example shown here was for a very specific radionuclide, Krypton-85, the calculational approach can be easily adapted to many pollutants or other non-radioactive atmospheric trace gases. The global modeling approach was relatively straightforward and did not require excessive computational resources.